Okay, so Coulombs law says if you have two charges in the universe, that's in your entire universe, they will create this force on each other. So F1 on 2, if these are both positive charges, the force of 1 on 2 will point away. It will point up at that angle and will have magnitude K, Q1, Q2 over their distance squared. F2 on 1, so the force on this charge from that charge will point the opposite direction. This is a third law pair. It will point back that way and have the same magnitude. What if we have a collection of charges? Well, these are vectors. All forces that we know of in nature follow the principle of superposition. So if I had some collection of charges, say we've got a positive, a negative, and a positive, and let's name them 1, 2, and 3. Then the force on 2, or let's say force of 1 on 2, these are like charges attract. So 1 is going to try to attract 2. Let me get some different colored markers here. And we'll point up like this as a vector. And that will have magnitude. Points like that as magnitude. K, absolute value of Q1, Q2 over that distance, the distance between 1 and 2 squared. This does not tell you the vector. This only tells you the magnitude. Vectors have an X and a Y and a Z if we're in 3 dimensions components. This tells you the magnitude. If I wanted to write this guy as a vector, I would have to find this angle here, theta, and I know the magnitude. So I've got some vector that points up at some angle theta. I want to break that into components. Here would be 1 onto X. There would be the Y component. This would be the magnitude, the hypotenuse. If I want to write this vector as a vector in component form, then I have to do some trig here and say 1 onto X would be that magnitude times the cosine of theta from the picture I've drawn here. The Y would be magnitude times the sine of theta. From this picture, remember when you're drawing out vectors, you always have to draw a picture, draw your triangle, use your trig to find the individual components. Then I would say as a vector, 1 on 2 is some vector, some X component, comma, Y component. 2 or 3 is also pulling on 2. So there would be another vector. These are likes attract. He would pull straight along here. So this would be the vector 3 pulling on 1. We're only worried about what's happening to charge 1. Or I'm lying, charge 2. That is, from our picture here, that's straight along the x-axis. That would have magnitude. K, Q3, Q2 over their distance, 2 and 3 squared. That's the magnitude of the vector. I'm not going to plug positives and negatives in there. I can see from my picture, from how I set up my axes, that's straight along the x-axis. So that guy's y component would be 0, and his x component would be the entire vector. Then the net force would be this guy as a vector added to that guy as a vector. So you have this problem coming up. This superposition of forces problem. This is the way to do this problem. Find each force as a vector in x and y components. Write them both down. Draw some triangles. Add the two vectors together. Find the magnitude of that net vector. Find the direction of that net vector. Remember, anytime somebody asks you for direction, you always have to give from something. Remember, never in physics will somebody say, give me the direction, and you'll say 20 degrees. 20 degrees from what? From the x-axis, from the y-axis, from downriver? So we got this scenario. I'm going to kind of help you with this problem. I've got my 2 microcoulombs. And -4 microcoulombs. I've got an equilateral triangle here. This is a 60-degree angle. And what were my distances? They were all the same. I think it was ½ meter. Yeah, 0.5 meters. We want to find the net force on the negative charge, this guy down here. I want to find the force on him. So I'm going to label these guys 1, 2, and 3. It doesn't matter how you label them. So I need to find F1 on 3 as a vector, the x component and the y component. You're going to have to do some work to find that. That might take you a quarter of a page. You want to find 2 on 3 as a vector. Write that as a vector. Use the picture to figure out directions, pluses and minuses. Coulombs law will only tell you the magnitude. Like you can see, these two are going to be attractive. So F1 on 3 is going to point back that way. F2 on 3 is going to point up that way. It's going to have some negative x component and some positive y component. You see that from the picture. Then the net force, F net, will be the vector sum of those two. Just add the x and y components. You get that as a vector, that'll be some x and y component. The question asks for the magnitude and direction of that. So you can see here, the net force is going to point, I don't know, maybe there somewhere. That's what F net will look like. Find the magnitude of that. You guys know how to find the magnitude of a vector. Find the x component, the y component, use Pythagorean. And then the direction, a lot of times people just want to do this. Theta is the arctangent of y over x. That will not give you the right answer. In fact, that'll give you a negative angle. Clearly, there are no negative angles here, because my x component is going to be negative here. So what I would do is actually use my knowledge of trig and finding angles, go through some work, find this angle right here. I'm going to call that, I don't know, maybe alpha, which will not be equal to theta here. It won't be equal to that, but it would be related to it. And then I would say my direction is alpha degrees, whatever it is, clockwise, or what are we, counterclockwise from the x-axis. Anytime somebody asks you for direction, you have to give angle from some fixed angle. You could give the angle from the y-axis. You could give the angle from the negative y-axis. Any of those are fine. But you have to tell me which one it is. Okay, so where does the electric force come from? What's the genesis of the electric force? It's this object called the electric field. Yeah, you can use I, J, and K. That's perfectly fine. You only have I's and J's. You won't have any K's, but sure. The force comes from the electric field. So I have in my universe right now, my entire universe is just a single charge located, let's say, at the origin. That one charge changes all of space. It literally bends space by a certain amount. Imagine kind of like a trampoline. This is the analogy we always use in gravity, and it's not a perfect analogy, but you could kind of think of it like you have some charge and it's warping space all around it. How much does it warp it? By this amount. The electric field, some distance r away from that charge, is kq over r squared. The electric field is a measure of the amount space has been stretched some distance r away. So I don't have anything else in my universe. There's no other charge sitting here. There's no force. It's just space has been bent by a certain amount. This is measured in newtons per coulomb. And it's a measure of how much force a charge that we put there would feel, even though there's nothing there. It's a force density. This is force per unit charge. There's the chat. Let me make sure I didn't miss a question. Oh, okay, I got that. So charges create electric fields which bend space. We can measure that. I could get my little measuring device out here and measure the electric field at that point. And the way we do that is we put a little 1 coulomb charge there. We call that a test charge. And we measure the force. We easily could measure forces, right? We have force meters. I measure how much force it feels, because this is the force per unit charge. Now, there's this debate in the physics community about whether the electric field is something that physically actually exists or whether it's a mathematical construct that we use to make the math easier. Related to the electric field is something called the electric potential that we're going to talk about in a couple of weeks. Like when you plug in something into your outlet and you say it's 120 volts, that's this guy. The electric field is the negative gradient of the electric potential. Gradient is like a 3D version of a derivative. So in a sense, the electric field measures changes in potential. So if I have an outlet and I say there's a 120 volt difference across that outlet, if I were to measure the distance across there, the electric field measures the change in potential per distance. The electric field's newtons per coulomb. V's in volts. V is in joules per coulomb. So there's some debate in the physics community over which one of these two is physical, which one actually exists, and which one is a mathematical construct based on the other one. You could argue that what's real is a change in potential, and then we're just taking derivatives of it. We're just measuring the derivative of it. How fast is V changing? The other point of view is, no, this one's real. This is the one that's physical. Space literally changes. And V is just an artificial mathematical construct. It's the antiderivative of E. I tend to, either way is appropriate. Either way is fine. I think the second way, because V is only defined up to an additive constant, whereas E is perfectly well defined. We're going to talk all about that in about 2 weeks. Just giving you some foreshadowing here. The electric field is also follows the principle of superposition. So if I have two charges sitting in space, this guy's creating an electric field that points out away from him. Say they're both positive charges. Electric field points away from positive charges. This guy will feel or create an electric field that points away from him. And those two will add together. So if I pick some spot in the middle, if those were equal charges, this guy's creating an electric field. He tries to bend space in that direction. This guy tries to bend space in that direction. Those would cancel out. And right here in the middle, we would get E equals 0. If I wanted to find the electric field down here, then from him, space got bent that way. From him, it got bent that way. Those will add together as vectors, and my net electric field would point down like this. So these two guys are glued in space. You might be asking, well, they feel a force. Why aren't they running away? Because I'm holding them down. They're stuck. I've glued them down and I'm letting them change everything around them. I want to ask what happens every place else because of those guys. We could do that in a discrete sense where we have 6 charges, 3 charges, 4 charges. Or we could do it in a continuous case where I have some charge, say, all smeared out in a disk. So instead of having individual charges, my charge is all smeared out. Well, now we're going to do the limit version of doing a whole bunch of sums. You guys have had calculus. What happens when you take something smaller and smaller and add an infinite number of things together? That sum turns into an integral over some dx or dy or whatever. Those are the complicated problems. Those are here. So there are the first 2 examples of finding the electric field from a continuous charge distribution. Those are the hardest problems we do all semester. I don't know, maybe Biot-Savart is a little harder because not only do we do this, but our solution's a vector, not a scalar. You definitely want to watch those videos well. You want to watch all of these videos. You will be doing that in this group assignment. You're going to have to use calculus here. I'm going to give you a little help on this next time. There's a chat. Yeah, okay. All right. So a few more minutes talking about electric field lines. Oh, yeah, we should point this out. I said it. I don't know if I wrote it. The electric field is the electric force divided by some second charge. Or alternatively, and I'm going to call this Q2. This is the relationship between E and F. So I have some charge Q1. It creates an electric field everywhere in space. It permeates all of space. It moves at the speed of light. If I were to wiggle this guy around, I would create wiggles in space, which we call light. That's what light is. Charge is moving around and that wiggles space. This charge by itself over here, some distance r away, creates an electric field. That field exists on its own. There's an electric field right here. If that's a positive charge, that points away. Now I come in, I bring in, this guy's glued down. I don't let him move. I bring in some second charge and I place it at that spot. What does it feel? It feels a force caused by the electric field that was already there. And that force will be his own charge times the electric field that was already there. That's where the force comes from, the electric field that already existed. That's really just Coulombs law. Remember, E was K Q1 over R squared. Now I'm just bringing in a second charge. That's what we wrote down for Coulombs law. Okay. So electric field lines show the field distribution from a fixed charge. So electric field lines point away from positive charges toward negative charges. Then if you have electric field lines and you bring in some other charge, that charge will want to point along an electric field line. Think of field lines like flow lines, like current lines in water, because the electric field is just a gradient of some scalar potential. So this is literally like you're watching current lines in water, and then you drop in a little boat in the water, then that boat will follow along the current. So if I've got some charge distribution here, these red lines are my electric field lines. If I bring in some new positive charge and drop it someplace, it will want to follow along one of these field lines. Positive charges move in the direction of the electric field. Negative charges move opposite the electric field. So if I were to drop a negative charge right here at this spot, it would move this way. If I drop a positive charge right here, it would move this way. Electric field lines never cross, and they flow out of positive charges back into negative charges. Look at these field lines flowing out of positive charges into negative charges. We call positive charges sources of the electric field and negative charges sinks. So you could literally think of this like water flowing. In fact, almost all of E&M was developed in terms of fluid dynamics. They literally thought there were fluids flowing. Think of this like you've got a water tap turned on, and over here is a drain. So water is flowing out from here, flowing across and draining back out of the universe over here. And then if you drop a little boat in, it will flow along these current lines. And when I say current, think water flowing. Don't think electrical current. We're not there yet. Okay, this particular charge distribution is called a dipole. That's when you bring a positive and a negative, bring them close together and glue them down. The most famous dipole, of course, is water, which of course looks like Mickey Mouse. This end has a net positive region. This end is a net negative region. The whole thing is neutral. This looks like an electric dipole. So then if you put it in an electric field, it will rotate. That's called torque on a dipole. This is how your microwave works. Things that you put in the microwave have water in them. We apply an electric field. We cause this to rotate. We turn off that field, it rotates back. That puts energy into the system, rotational energy. And energy just gets translated into heat.